In the Real Climate blog, run by a team of high-level climate scientists, they recently hosted a discussion on the theme that the science is not settled. In this final commentary in our overview series, we're going to be looking at a couple areas where the science is still not settled. We mentioned earlier that climate models are not very good at simulating cooling temperatures unless they're caused by volcanoes. Now, in fact, it is quite well known that changes in the pressure, wind direction and currents in the South Pacific can lead to both higher temperatures and lower temperatures globally. These are known as El Niño if they lead to rising temperatures, and La Niña if they lead to falling temperatures. Whilst the effect of these changes in the Pacific are well known, what is not understood at all is how they occur. In this graph, we're going to look at another area where science is still not settled, and we'll be looking at the Milankovitch cycles. These are named after a Yugoslav astronomer who developed them in the 1920s and 1930s. There are in fact 3 cycles which relate to the orbit of the Earth around the Sun. Sometimes the orbit is almost circular, sometimes it is slightly elliptical, and the Earth cycles between the two on a frequency of about once every 100,000 years. The angle of tilt of the Earth also varies from about 22 degrees to 25 degrees, and it does this on a cycle of about 41,000 years. The direction of the tilt relative to the Sun also changes on a cycle of 23,000 years. Moving now to the details of this graph. The red line shows the temperature as measured from the Vostok ice core. It is given in degrees Celsius relative to the present temperature. On the vertical axis, we give the radiation as calculated from the Milankovitch cycles in watts per square meter at 65 degrees north in July. As you can see, there is quite a lot of agreement between the changes in temperature and the changes in radiation. For example, here you can see that there's a very clear peak in the radiation as calculated from the Milankovitch cycles and a clear peak in temperature. Here also, we are in our present interglacial. You can again see that there's a very clear peak in the Milankovitch cycles and in temperature. And at some of the intermediate points, here and here, here and here, here and here, you can see that the peaks as calculated by the Milankovitch cycles also correspond to peaks in temperature. Not only do the peaks coincide, but the troughs also often coincide. It's obvious that there's not a perfect coincidence between temperature and radiation. For example, here, quite a high value of radiation occurred, but only a relatively small increase in temperature. Despite these limitations, it's fully accepted that the Milankovitch cycles drive the sequence of ice ages and warm interglacials. What is not clear is how they do it. Here we've plotted the radiation at 65 degrees north in July. If you plot the radiation over the whole Earth for the whole year, the variation is very much less. So it's quite significant that something special happens round about 65 degrees north. It may be the fact that at 65 degrees north, a bigger proportion of the Earth's circumference is covered by land than elsewhere. It might be to do with the nature of the vegetation there, the fact that the difference in the reflectivity of snow and the pine trees that you get there is very high. It might be something in the northern oceans. Nobody knows, and this is one of the other big areas of uncertainty in climate science.